Today, in my lecture of this series of chemical thermodynamics, I shall discuss the Joule-Thomson expansion. It is also called the Joule-Kelvin expansion. This expansion is very much important for cooling down a fluid. That fluid may be gas or may be liquid which has having the flowing ability. And in case of gas, this experiment is very much useful for cooling down this gas. And you all know this cooling down of this gas leads to liquefaction of this gas. So when its temperature becomes below its critical temperature. And you see in this picture, this is the cylinder, and cylinder is properly insulated, and there lies these two pistons. The pistons are also insulated, and the pistons are weightless, frictionless, and horizontally movable. And in the left side of this porous plug and the piston, it contains 1 mole of this gas, volume V1, pressure P1, and temperature T1. And the external pressure is P1. In the right hand side, this piston is under this pressure P2. P1 is greater than P2. So this gas will move. The gas will flow from this left hand chamber to this right hand side chamber through this porous plug with a difficulty. And since this gas is moving with a difficulty, flowing with a difficulty, this is also sometimes called the throttle expansion. Throttle expansion. Throttle expansion. And whenever the gas passes through this constriction, and here it is the porous plug, or you can say this small capillaries, small dark capillaries are fused together and placed here, or highly compressed some cotton pack may be there, or say earthen plate may be also placed here. It is some sort of like this faucet in this latrine, or you can say this head shower, when this water is moving from this higher pressure to lower pressure, and here also this gas fluid moving from this left hand side to the right hand side, pressure is under the pressure is P2. And the piston moves as the gas moves to the right hand side. The piston moves from this position to come in contact with this porous plug, and the gas takes this volume V2 and this pressure P2 and temperature T2 when it is passed through this porous plug. And here one pressure gauge is kept. Here also one pressure gauge is also kept to monitor this pressure P1 and P2. Here is one thermometer, and here is another thermometer to record the temperature, and this is the pressure gauge. So this is the total arrangement, and this gas moves very slowly, and each side the pressure equilibrium is maintained. Whenever those process is slow, but still it is called the irreversible process, as this gas flows, or the fluid flows against the constant pressure P2. So this is the experiment. This is the experiment, and the effect, Joule-Thomson JT effect. Let us discuss this. What is the effect occurring whenever the fluid is flowing through this porous plug under this insulated condition from higher pressure to lower pressure. It is mostly seen that in most of these cases the gas cools down whenever it is flowing through this constriction, means T2 becomes less than T1. Only hydrogen at ordinary temperature pressure, only hydrogen and helium they will baffle this general trend, and in these two liquids at the room of these two gases at the room temperature pressure, this T2 is greater than T1, means these two gases are heated up. So this is the effect, and this fall in temperature when the gas moves through this porous plug under the insulated condition, temperature changes, and this is the effect. And next I shall call one is inversion temperature. Inversion temperature. Every gas is having inversion temperature. It is the temperature above. It is the temperature, this initial temperature when kept at this above this temperature, there will be heating effect. Only the gas cools down whenever the initial temperature is below the Ti. When this gas initial temperature is equal to Ti, there will be neither cooling nor heating. So the inversion temperature for cooling down a gas plays a very important role. And for hydrogen and helium, hydrogen for Ti, for hydrogen and Ti for helium, and in this case the inversion temperature for these gases are very low. It is suppose say 254 Kelvin, it is 47 Kelvin or like that. Of course, I can show the inversion temperature depends on this initial pressure by which the gas actually expands. So next I like to discuss the thermodynamic condition. Thermodynamic condition for the experiment. Thermodynamic condition for the experiment. From the first law we know this Q plus W is equal to del U. Q is the heat transfer in between the system. This is the whole system and the surroundings. W is the work done on the system, and delta U the internal energy change of this gas for this expansion. But in this case, since it is properly insulated, so Q equal to 0. So W equal to del U. and W in left hand side there is a volume change, right hand side in also volume change, so it is the pressure volume work. So whenever this W is a pressure volume work, it could be represented as minus P1, and the volume changes from V1 to 0. P1 remains constant. P1 has been kept a constant, and dV volume V1, and when the piston moves at this position, the volume becomes the 0. And this one again minus, and V2. V2 is constant, and it is the dV volume then 0. From 0 the piston moves here at the initial positions, and then it is passing away towards the right hand side to have this volume V2, and this one equal to this delta U means U2 minus U1. U2 is the internal energy of one mole gas after passing, and U1 is the internal energy of this gas before passing. So this left hand side is minus plus P1 V1, and it is minus P2 V2, and this one equal to U2 minus U1. So if we change side change, if we make a side change, then U1 coming here, then U1 plus P1 V1 is equal to U2 plus P2 V2, and we know U plus PV equal to H. So here this enthalpy H1 equal to H2, or you can say del H equal to 0. It means that the process, by this process enthalpy remains constant, and so this is why it is called isothalpic process or expansion. Isothalpic expansions. I can remember the Joule's experiment, Joule's free expansion. In case of Joule's free expansion, it has been shown that the internal energy remains constant during this expansion. Here, the enthalpy remains conserved in this Joule-Thomson expansion. So this, but since the process is irreversible, one is not entitled to say during this process enthalpy remains constant or not. It is the equilibrium state, initial equilibrium state. After again it attains equilibrium, and at this whenever at this initial state this enthalpy is H1. After again whenever this state gas attains equilibrium, it is H2, and these are the 2 points. If we plot this total expansion in a diagram, then we shall get only the 2 points, initial point H1 and final point H2. In between these two, we do not know what is the enthalpy in this intermediate stages of this expansion. So this is the isothalpic process. Now I like to discuss Joule-Thomson coefficient. It is seen from this experiment, this one mole gas changes this pressure from P1 to P2. P2 is the final pressure, P1 is the initial pressure, temperature T2 the final temperature, P1 is the initial temperature, and there occurs the change in temperature when it is passing through this high pressure to lower pressure. We like to quantify how much the change in temperature occurs in this expansion by this fall in pressure from left to right. So this quantity we can call this Joule-Thomson coefficient and denoted by mu Jt, and mu Jt is defined as del T divided by del P at a constant h, or you can say this T2 minus T1 divided by P2 minus P1, and it is at a constant enthalpy. So, or in short, we can also write mu Jt equal to del T by del P at a constant h. What is the definition? It is the change in temperature for the change of unit change of pressure of these two sides at a constant enthalpy, means at this Joule-Thomson expansion. So P2 P1 is always greater than P2. So this del P equal to P2 minus P1, and this one is the negative always for this expansion process, and this del T equal to T2 minus T1, and when T1 is greater than T2, T1 is greater than T2, then this one is also the negative, and the ratio of the two, that means mu Jt equal to positive. Mu Jt positive means whenever this gas expands from this high pressure to lower pressure through this porous plug, there is a fall in temperature. Fall in temperature means T1 initial temperature is greater than the final temperature, and it is called the cooling effect. It is called this cooling effect of this gas. Again, when T1 is less than T2, T1 is less than T2, means T2 is greater than T1. So this one is positive, this one is negative. So ratio is negative. So mu Jt in this case is a negative, and this is called heating effect. This temperature is warmed up after passing through this porous plug. The gas is heating up or warmed up after passing through this. When T1 is equal to T2, then mu Jt equal to 0, means no effect. When T1 equal to T2, this term equal to 0, and in this case this gas will undergo neither heating, not cooling. So this sign of mu Jt dictate whether the gas is cooled down or heated up, or there occurs no effect. And actually this sign or these effects depend on the temperature or the inversion temperature of this gas. It depends on this initial temperature of this gas. We can draw a scale. Say scale could be like that. Here this T, and this is the T equal to inversion temperature, and at this inversion temperature mu Jt equal to 0, means no effect. when T is less than Ti, mu Jt is greater than 0 means positive. Greater than 0 means positive. It is negative means less than 0. It is equal. So here the cooling effect. And when T is greater than Ti, mu Jt less than 0 means negative, and it is the heating effect. So according to the initial temperature of this gas, whether it is equal to the inversion temperature or less than inversion temperature, greater than inversion temperature, the nature of the effect will prevail. Now I shall try to explain why this Joule-Thomson effect, why and how the Joule-Thomson effect depends on the temperature, initial temperature of this gas. So this one I can do in a mathematical way in order to explain the temperature dependency of this Joule-Thomson effect for this ideal gas and for this real gas. And you know this H enthalpy is a function of temperature and pressure. Temperature and pressure. So this dH means a change in enthalpy. This will be a del H by del T at a constant pressure into dt, and plus it is a del H by del P at a constant temperature, and it is dP. So this is the change of enthalpy with the change of temperature when pressure fixed, and this term is the change of enthalpy for the change of pressure when temperature fixed. Sum of these two will give you the net change of this enthalpy for this process. But this process is isoenthalpy, means dH equal to 0 for this Joule-Thomson expansion or Untitled expansion. So this one equal to 0 equal to, and this term is very popular. This is called this Cp. Cp means molar heat capacity of this gas at constant pressure, and it is dt and plus del H by del P at constant T into d. So side change, taking a side change, we can write del T by del P at constant H equal to minus 1 by Cp and into del H by del P at constant temperature. This one is actually mu Jt. So mu Jt, Joule-Thomson coefficient, is given this minus 1 by Cp and del H by del P at a constant T. This is also an expression of this mu Jt, though this expression is not used for this calculations of mu Jt of a gas. However, this one, if we can determine this mu Jt and Cp, we can get this enthalpy dependency, pressure dependency of this enthalpy in constant temperature. So as you see, this del H divided by del P at constant temperature is equal to minus Cp into mu Jt. You can remember, in case of Joule's experiment, it is del U by del V at constant temperature, and instead of Cp, in that case, it was Cv, and it is mu J, Joule's coefficient. So if we know this Cp and mu J of a gas, then this one could be calculated. Suppose Cp is equal to this Cp is equal to 8.9 calorie mole inverse and Kelvin inverse, and this mu J and this one minus, and mu J equal to 1.144, and it is Kelvin and atmosphere inverse. So if we do these calculations, we should get 10.2 calorie mole inverse and an atmosphere inverse. So this one, this is a very easy problem, very often set in different competitive examinations. Cp and mu J known and del H by del P. That means with this increase of pressure, this enthalpy will decrease per unit increase of pressure. This enthalpy decrease by this amount per mole. Now I can write H equal to U plus P. So here if we put then mu J equal to minus 1 by Cp, and here del U plus PV and divided by del P at a constant temperature. Or I can write here elaborately mu J equal to minus 1 by Cp, and here del U by del V as internal energy is a function of volume. So here it is a T, and since it is written del V instead of del P, we can multiply here del V by del P at constant temperature, and this is the first time plus minus 1 by Cp and del PV by del V at constant temperature and bracket close. So this is the first term, and this is the second term. This is also another expression, though not used practical use, but this helps to explain the temperature dependency of this Joule-Thomson effect. When there will be cooling, or when there will be heating, or when there will be no effect depending on this temperature. So let us consider one for ideal gases. For ideal, let us see what happens for this ideal gas. For ideal gas, del U by del V at constant temperature equal to 0. So this is 0. 0 means this first term. This first term equal to 0. And in case of ideal gas, PV is constant at a given temperature, which is Boyle's law. So del PV divided by del P at a constant temperature, this is also equal to 0, and second term also equal to 0. So first term 0, second term 0, sum of the two equal to 0. So mu J in this case mu J equal to 0. It means that if this ideal gas have been taken here and undergoes this Joule-Thomson expansion, there will be no change of temperature, there will be no effect. Then let us see what happens for this van der Waals gas. Or let us consider what happens for this for the real gases. What happens for this real gases? This one can be written as mu Jt equal to first term minus 1 by Cp into del U by del V at constant temperature into del V by del P at constant temperature, and this one, and second term is minus 1 by Cp and del PV divided by del P at constant temperature, and this is the second term. Now I shall consider the what happens for this real gases. For real gases, this is the 2. For the real gases, actually this del U by del V at constant temperature is positive always. Positive always. Already I have shown that this value for this van der Waals gas is A n square by V square. A square by V square, all the terms are positive, so this one is positive. Other equations, the gases which are obeying these other equations, in that case also this del U by del V at constant temperature is positive. And del V by del P, del V by del P at constant temperature is always negative. Always negative. At a given temperature, if the pressure is increased, then volume will be decreased. So it is negative. So this is positive, positive and negative. Here is negative. So first term is positive always. Always. Now let us consider the second term. In case of second term, this to have this sign of this value of this term, let us consider the Avogadro car. Here it is P, and here it is the PV, Avogadro car. A M A G A T, Avogadro car. For this ideal gas, this will be like this ideal value, or the ideal value or ideal gas. In case of real gases, PV versus P will never follow the constant one at a particular temperature. It becomes like this. At low T means the PV decreases, attains a minimum and then increases. And whenever the high temperature at high T, this PV value increases from the start with the increase of P, and this one is this scale has been condensed, and this pressure is about 200 to 300 atmosphere here. So from this graph we can conclude what will be the sign of this term, of the second term. So at low T and moderate pressures, moderate P, that means up to this pressure, this PV decreases with this increase of P. So del PV by del P, this slope it becomes negative. Slope becomes negative. So it means that PV decreases with this pressure up to this certain moderate pressure, which is about the 3 to 400 atmosphere. So this second term, in this one is positive, this one is negative, and here is negative. So second term is also positive. First term positive, second term positive. It means that at low temperature and moderate pressure, the gas suffers a cooling effect whenever it is passing through this porous plug. Now I shall consider at high second at high T and moderate pressure, moderate P. This PV increases with this increase of P from this very beginning, and so in this case del PV by del P at constant temperature is equal to positive always. So the second term, in this case second term equal to positive, second term negative, second term negative. Since this is positive but this one is negative, so second term is negative. First term positive and second term negative. Whenever this negative term exceeds the value of this or dominating the first term, this mu J becomes negative. So in that case, mu J becomes negative, means there will be heating effect at this high temperature and the moderate pressures. So in between the low temperature and high temperature, there must be one temperature at which this mu J equal to 0. Mu J becomes equal to 0, and that temperature we call this inversion temperature, below which there will be cooling, above which there will be heating, of course at moderate pressures. At this inversion temperature there will be no effect. But one thing I can mention, I should show also, whenever the pressure is very high, and even at low temperature, whenever the pressure is very high, then this term also becomes positive, this will be positive, and this one is negative, and this, when this term exceeds this term, means negative becomes negative. So at a very high pressure, mu J is negative always, or there will occur always the heating. Now I try to develop an expression for calculations of a mu J of any gas, and this one is very useful. And you say mu J having this expression, this one. But the second equation, thermodynamic equation of state, thermodynamic equation of state, which is equal to del H by del P at a constant temperature, is equal to minus T into del V by del T at constant pressure plus V. This has been shown while I have been discussing the Maxwell's relations. So this is the thermodynamic equation of state, second thermodynamic equation of state, involving this del H by del P at constant temperature. If we put here this term, then expressions of this mu J becomes 1 by Cp, and here T and del V by del T as constant pressure and minus V. And the right hand side of all the terms are determinable, and so this one is a very useful expressions for this mu jet. Cp could be determined by means of calorimetry. This one also could be determined, and T is also determined by means of temperature. It is the initial temperature, it is the molar volume, initial molar volume. So all these things on the right hand side could be determined. Let us see what happens for the ideal gas. Ideal gas. Ideal gas obeys this equation, PV equal to RT for 1 mole of this gas, and so V equal to RT by P. So del V by del T at a constant pressure equal to R by P. So if we put here, then mu J equal to 1 by Cp, and here T is to be multiplied here, then RT by P, RT by P minus V equal to 1 by Cp, and V minus V equal to 0. Means in this case also I have shown this mu J equal to 0 for this ideal gas. Means ideal gas will suffer no Joule-Thomson effect. And the second one, if we consider the for this gas obeying P into V minus V equal to RT equation. And in this case, this V minus V equal to RT by P, and so V equal to RT by P plus B, and so del V by del T at a constant pressure, this term to be calculated at constant pressure equal to R by P and 0. This constant whose differentiation with respect to temperature equal to 0. So this one mu J T equal to R1 by Cp, and it is RT by P minus V. If we put RT by P equal to V minus V here, then V will cancel. So this will be equal to minus V divided by Cp. V is positive, Cp is positive, here it is negative, so this term is a negative. So mu J having the value minus V by Cp and its sign is negative, means this gas when you are passing through this Joule-Thomson expansion, there occurs always a heating. And the third one, very important one, the gas which obeys this Van der Waals equation. The gas which obeys the Van der Waals equation in for Van der Waals gas. So the equation is P plus A by V square into V minus V equal to RT. So this term very difficult to calculate by this from this Van der Waals equation, as V remains in a very complicated way, and so we shall have to take some approximations, as I have already done in case of Cp minus Cv for this Van der Waals gases. So in this case, if we multiply full, then it will be Pv minus Pv plus A by V minus AB by V square equal to RT. So these three terms are the correction terms, and the values of these correction terms are very small. So in this case, we take this approximation that the V we can replace here by using this ideal-gas equation, V equal to RT by V. This approximation have to be made in order to simplify this problem. So this one is PV minus PV plus AP divided by RT and minus AB P square divided by R square and T square, and this one equal to. If we divide both sides by P, then it is V minus B plus A by RT and minus AB P divided by R square and T square equal to RT by V. So now V equal to RT by P, RT by V plus B minus A by RT plus AB P divided by R square T square. Then if we differentiate this del V by del T at a constant pressure, then this one equal to R by P, first term, second term 0, and third term plus A by RT square, and this third term minus twice ABP divided by R square and T cube. If we multiply by T, then T into del V by del T at a constant pressure equal to RT by P and plus A by RT and minus twice AB P by R square and T square. One T will be cancelled. So instead of writing this RT, the value of RT, if we put this one instead of this RT by P, then it will be equal to V minus B and plus this one twice A by RT and this one minus 3AB P divided by R square T square. So this mu J and V to be bring out in here in this side. So T into del V by del P at a constant pressure minus V equal to, we can write twice A by RT first minus B plus minus B and minus 3 AB P divided by R square and T square. So this mu Jt, the expressions of this mu Jt equal to 1 by Cp, and instead of this one we can write this twice A by RT minus B and minus 3 ABP divided by R square and T square, bracket close. So this is the expression of mu Jt for this gas obeying the Van der Waals equation. and our equation. At the north, at low to moderate pressures, moderately, this term you can neglect. So whenever this term is to be neglected, then it becomes very simple. Mu Jt equal to 1 by Cp into twice A by RT minus B only. This result signifies that as the temperature is decreased, the mu Jt is increased. A, B are fixed. Cp also fixed for a gas. And in this case also you can see the mu Jt depends on temperature and pressure. Initial temperature, initial pressure of this gas, and AB, these are the characteristic constant of this gas. So mu Jt depends on temperature, pressure and nature of the gases. And whenever this one is elevated, this is coming, and you can see with the decreasing temperature. If we go on passing this, several porous barriers are there which has been done industrially. Then the gas cools down and T is decreased. As the T is decreased, the mu Jt is increased, means the more effective the Joule-Thomson effect will be there. For a same drop of pressures, there will be more change of more fall of temperature. So again, if we say plot if we plot 1 by T and here mu Jt, then it will be a linear plot, and this will be like this, and it is 0. So this one will be minus B by C, and the slope will be equal to twice A by R Cp, and this one is in this case mu Jt equal to 0, and so this point will be 1 by Ti. This point will be 1 by Ti, means the reciprocal of this inversion temperature. By this simple expression, we can show how and also give some explanation how the temperature effect on this mu Jt is occurring. Say 1, when T is less than, you can get an expression of this Ti also. When this T equal to Ti and mu Jt equal to 0. So putting here, we can get this Ti equal to twice A by Rp. So we get an expression of this inversion temperature of this gas. So if we know this A and B, these two constant and our constants of that gas, and it could be this sort of problem is very easy to solve. So the number of cases will be there. Suppose 1. When T is less than Ti, means initial temperature is below the inversion temperature, then T less than twice A by Rb, or we can get B less than twice A by RT. Twice A by RT is greater than B, so Cp is positive, then mu Jt is positive. Means the occurs a cooling effect. So this nicely shows that whenever the temperature below the inversion temperature, mu J becomes a positive and cooling effect occurs. And in case of the second, when T is greater than Ti, then T is greater than twice A by RB, or you can say this B is less, B is greater than twice A by RT. When B is greater than twice 2A by RT, this mu JT will be E JT will be negative. Negative means heating. Whenever the initial temperature is greater than the inversion temperature, this gas will be heated up. And when T equal to Ti, then T equal to twice A by RB, or you can say B equal to twice A by RT, and mu J equal to 0. B equal to twice A by RT. So mu J equal to 0 means no effect. This form nicely these calculations nicely show that how this inversion temperature makes an important effect on this sign of mu J, when it will be cooling or when it will be heating or like that. If we make a general expressions for this fluid, suppose the fluid whose equations are not known, in that case this could be expressed in terms of this alpha. Alpha is the cubical expansion coefficient, and this one equal to 1 by V and del V by del T at a constant pressure. Or this equation you can write this mu J equal to, suppose you are multiplying this V by Cp, and here it is T, and then it will be V and del V by del T at a constant pressure and minus V. So this one actually this value is alpha. So this one we can write V by Cp into alpha T minus 1. This is 1. V is taken out. So this is a very important expressions of mu J for any fluid whose equations we do not know. Only we calculate this alpha and the temperature, initial temperature. It is the initial molar volume, and Cp is the constant pressure, molar heat capacity, and by this way. And again when T equal to Ti, this mu J equal to 0. So if we put here, then simply this inversion temperature becomes equal to 1 by alpha. So if we determine this alpha, then we can get this value of the Ti. This is the simplest. By neglecting this term, we get this mu J equal to this one. It is very clear that whenever this temperature is lower than inversion temperature, this intermolecular attraction dominates over this V side effect, and mu J is positive. But above this inversion temperature, this side effect is greater. then the intermolecular attraction effect of these gases, and so mu J(T) is negative. And when this at this inversion temperature, both these two, this intermolecular attraction balances the side effect, and this mu J(T) equal to 0. This is the simplest way to represent this mu J(T). And now I like to show a very important case where for a gas there might be more than one inversion temperature. So if at say at high pressure, at moderate to high pressure, high P, this term you cannot neglect. And if you keep this term, then mu J(T) will be like that. And I have already said that mu J(T) depends on temperature, pressure, and nature of these gases. So when in this case also, when T equal to Ti, mu J(T) equal to 0. So putting here this one equal to 0, 0 equal to 1 by Cp, and it is twice A by RTi, and minus B, and minus 3 ABP divided by R square and T square, Ti square. Here the T becomes the inversion temperature. So it is Cp is not 0, so this term within the bracket equal to 0. So we can rearrange this one as B Ti square and minus twice A by R into Ti, and this one plus 3 ABP divided by R square equal to 0. This is very popular one. BTi square minus 2A by RTi and plus 3 ABP by R square equal to. So this is the quadratic equation of Ti. Quadratic equations of Ti, and so this Ti will have two roots. One is called the upper inversion temperature, and another is a lower inversion temperature. Upper and lower. So a gas is having the two inversion temperature. One is the upper one, and this is the lower one. And this, whenever you are calculating from this equation, this Ti equal to twice A by RB, then this will show this upper inversion temperature of this gas. So in this case, you can also see the Ti depends on pressure. This Ti and P, they are interrelated. So if you draw this curve, how this inversion temperature depends on this pressure, depends on this initial pressure of this gas, then you can see, suppose it is the P is plotted along this x-axis, and here mu J is plotted along this y-axis. This curve, here this is the Ti. Ti is plotted along this y-axis. This is the equations of this parabola. So this equation becomes this one, parabola, and in this line mu J(T) equal to 0 means pudding. And inside this one, this mu J(T) is equal to is greater than 0, positive, and it is no effect. Here no effect on this line. Here the cooling effect. and outside of this parabola, this is the heating effect, or mu Jt. Mu Jt is less than 0, negative, and cooling effect. Heating effect. Heating effect. So this one is the cooling zone. This one is the cooling zone. At any given pressure, suppose this is the pressure, at this P is the initial pressure, at this given pressure, we are having this two inversion temperature. This one is the upper Ti, and this one is the lower Ti. Lower Ti. And in case of experiments with this nitrogen, this same sort of curve is also obtained. And in this case, this curve could be like this one, experimental. This is the experimental curve. This one is the experimental curve for this nitrogen. Curve for the nitrogen, and this one is the van der Waals for van der Waals gas, van der Waals for nitrogen gas. We can also, if you like to do, then you can also calculate this inversion temperature whenever A and B and pressure is known. Suppose for a gas, or a van der Waals gas, A equal to 1.4 atmosphere and liter square, mole inverse 2, and B equal to 0.04 liter mole inverse, and P say 10 atmosphere. Say 10 atmosphere. Then R will be equal to 0.082 liter atmosphere and mole inverse and Kelvin plus. If we put all these four quantities in this equation by using this Sridhar-Acharya formula, you can calculate this inversion temperature. And we are having these two inversion temperature. In this case, it is the 800 and 46.4 Kelvin, and this one is the 7.4 Kelvin. And if we do these calculations, then it will be equal to 853.6 Kelvin. So actually this calculation shows that this one gives you the upper Ti more or less, and this one could be neglected. It is very, very low. So in case of inversion temperature, we always refer to this equation, this expression. The last one I like to say, what is the difference between this adiabatic cooling and the Joule-Thomson cooling? Adiabatic cooling and Joule-Thomson cooling. What is the difference? Already adiabatic cooling and Joule-Thomson cooling. It is already been shown that adiabatic cooling occurs for both the ideal gas and also this real gas. And adiabatic cooling is adiabatic expansion leads to the cooling of this gas due to the decrease of this internal energy. Whenever this work done by the gas, it becomes minus del U, internal energy decreases whenever expansion occurs. And however, JT cooling occurs also due to the decrease of this internal energy, but this internal energy is coming from this intermolecular attractions. Ideal gas will not go the Joule-Thomson cooling, and only the real gas which are having the intermolecular attractions, so this real gas will suffer this JT cooling, and that is also even when its initial temperature below the inversion temperature. This temperature becomes less than inversion temperature. But in this case, there is no temperature restriction, temperature variance at all temperature, adiabatic cooling occurs. So this is all about the actually whenever the gas expands, the molecules are being separated, and some amount of work of this gas has to be done to overcome this intermolecular attractions, and whenever this gas does some work, this temperature falls. This is the case in case of this Joule-Thomson cooling. So this is all about in details about the Joule-Thomson effect. I have discussed fully the Joule-Thomson JT effect, JT inversion temperature, and also some problems. In my next class, I shall try to explain the Clapeyron equation, which is also very important, the temperature dependence of this transition point. So thank you all who are watching this video. It is a this video is of long duration and naturally not very easy to follow all along. I should thank to those viewers who can very patiently follow this sort of lectures. Thank you all.